Hello, everyone. So we'll be talking about the Diels alder reaction. I'm figuring out that the best way to explain this mechanism is to build a molecule too, so that you can have an idea, especially if you don't have a kit, a chemistry kit, to build a molecule. All right. So let's start with this. Imagine that the professor is giving you this on the exam. It's like the professor says, predict the product. Okay, first step I would do, okay, let's determine what energy we will need to close the ring. Because, quickly, some terminology, I'm expecting you to know that, but in case you haven't done this yet, so if you see that I mentioned, let me just say that. If you see that I mentioned diene and dienophile toward the video, the only thing I want to say is that diene, this is a diene, means two, like you see die, two in, two double bond. This is a double bond, this is a double bond, or that one is a double bond, right? Diene. This molecule here is a dienophile because it has one bond. Now, yes, there's a CO bond, but we don't really care about the CO bond, in, like for alkene, it's really CC double bond, right? So this is a dienophile. That means it is file. It is a diene lover, electrophile, electron lover. Anything with file, basically, is lover of whatever that was prefix we had, right? Again, the only thing they say is in a cycloaddition, let me use pseudo space. A diene and a dienophile come together to form a 6-member ring, a cyclohexene. Okay? Why? Because we will have a nice interaction here where we will have some out. It's like a nice concerted mechanism, right? Here and that one here. Okay? We'll come together and close that ring, right? Now, if it was 8, that would be nice, but it's not the whole story, because sometimes or diene and dienophile can have group on them, like this one, and it's good to have group because they strengthen the reactivity of the diene and the dienophile. So in our case here, we have some group, we know the orientation at the end will matter, the stereochemistry will matter at the end. So let's do this. First, determine the energy needed to even close the ring, because what happened is that HOMO of one will get together with the LUMO of another one. If you don't know the term, it's good to go review, Highest molecular orbital, lowest molecular orbital, HOMO, LUMO comes together. To do that, we will need either heat, either light. The way to determine which one it is to follow the rule. The rule say that if the number of electrons that will be involved in that mechanism can be obtained using 4n plus 2, then it will require heat. If it's 4n, it will require light. What do I mean? Let's apply this rule, right? We agree that this is how we will be closing the ring. Let me put it in the color, right? Again, we don't really care too much about this group. Let me put it aside for a second. Molecular will do that, but I just want you to see what exactly is interesting us. 1, 2, 3, 4, 5, and 6. A 6-member ring with this backbone here. Okay. And all right. So let me place this metal group back. Let me resize it a little so it doesn't really interfere with my drawing. Here it is. All right. Okay. Now that's the dance that we will have. This electron will do this bond, we'll have this, we'll have this. Okay, all right. Which means that in the dance or nice dance here, 1, 2, 3, 4, 5, 6 electrons will be involved in that mechanism. So quickly, let me write down 6 electrons will be involved. Now, is the number 6 can be obtained using 4n plus 2 or 4n? Let's see. Usually I memorize only one of them, one row. I like to memorize this because it looks nice, right? For n+2 thermo, which means that on the exam, when the professor brings that sheet quickly, once I receive that sheet from the professor, my exam sheet, I write for n+2 thermo, and of course, I know it's cycloaddition because we will have something else for pericyclic, other thing, right? Cycloaddition, I know it's gonna be 4n+2 thermo. And for I just memorized one. And I'm like, okay, you know what? Let me put a little y here so that you can see what's going on. But guess what, guys? There's no y in real life. For n+2 thermo. For n+2, we know that the target is 6, right? Target 6. N can be any integer from 0, 1, 2, 3, any integer, right? To infinity, I guess. If n equal to 0, then y will be equal to 2. If n equal to 1, then y will be equal to 6. Amazing. I got 6 using 4n+2. Then it should be hit because 4n+2 is a thermal reaction. Now, guess what, guys? You could have memorized the other one too, 4n light. Let's try this. Imagine that you choose to memorize 4n light. Do the same thing. If n equal to 0, y, let's put y here, equal to 0. If n equal to 1, y is equal to 4. If n, remember the target is 6 electron. If n equal to 2, y is equal to 8. No, you see how we already left 6 behind? 6 doesn't even apply to 4n, which means that I know that it would be 4n light. It has to be the other one, the other energy heat. I hope it makes some sense what I'm saying, okay? All right. Once you determine the energy needed to close your ring, now let's determine the orientation that we're gonna need. In reality, in the solution, this is what's happening. Everything is moving, right? We don't know. Guess what? The molecule can do this, click together. The molecule can do that, click together. We don't really know how it's gonna come. Can be upside down, however, you see there's one flipping like the back of my hand too is a way. We don't really know, but there's a nice pattern we can, nice set of rules we can apply to get to the answer. First, let's determine the effect the group attached to the diene and the dienophile will have on the overall molecule, right? Okay, on our diene, after this group here can do resonance, look at this, guys. At some point in time, this oxygen can donate its electron here. You can have that, right? So at some point in time, we will have this resonance structure, right? Okay. At another point in time, let me put it in pink. Oh, green. We can have this. Oh, no, sorry. Or on this carbon here, we'll have that one here. So if we number them, oh, of course, we will move this and form that bond here. But again, I hope you see what I mean. Let me remove this now. Let's number our carbon. 1, 2, 3, 4, 5, and 6. I already put 5 and 6 here. 5 and 6. We know that at some point, let me reconstruct my diene. I know that after doing resonance, guys, I know carbon 2 will have a partial negative charge, while carbon 4 will have a partial, no, they both will have a partial negative charge, okay? Which means that this group, OCH3, is an electron donating group, because you see how it donated its electron 1 and it pushed all the electron 1, leaving carbon 2 and 4 with a partial negative charge. Let's go on our dienophile now. I'm gonna use resonance again. I know this bond can donate some electron to oxygen. So at some point in time, I will have, you know what, I like to, let me just do this. Draw the resonance on the side. I will have this, right? Leaving this carbon here with a partial positive charge. Oh, I forgot to draw the bond here. And at another point in time, we can do another resonance like this, right? Leaving carbon 5. Remember, this one was 5, right? Of 5. So that's carbon 5, that's carbon 6. So we'll have carbon 5 with a partial positive charge. So let me put partially positive. Oh, why is it so thick? Partial positive charge. That's the goal of this experiment, to find the partially positive and partially negative charge on a carbon of interest. When I'm saying carbon of interest, the one that will really contribute in closing that nice ring, right? To do this mechanism. Carbon 5 has a partial positive charge, and I hope it makes sense, guys. Carbon 5 with a partial positive charge, while carbon 4 has a partial negative charge. All right. Once you determine the charges, now we can talk about the orientation, right? In a needle picture, I'm just gonna do the same thing. Let me quickly, I just want it to be neater so that you can see what's going on, right? I'm gonna give this one carbon 2 partial negative, carbon 4. Oh, I forgot my metal group here. Okay, with carbon 5 being partially positive. Okay, which means that, guys, in the solution, the whole point, even when it's moving like this, like, you know, the two molecules are moving, but I can do this two at the same time. We know that this molecule will tend to stay in that orientation. Why? Because the whole point is that we're trying to make close charges interact as much as possible. This one isn't gonna interact with this one. Why would it interact? Why would carbon 5 interact with carbon 2? You know, it's true, negative, positive attract. If carbon 4 is reading right there, it's so close, we know the interaction will be there, which means that it will most likely stay in this conformation so that 4 and 5 can nicely interact together. So I mean, what we determine here is that while dancing everywhere, at the end, the molecule, at the end, the product, we should notice that OCH3 and this ketone group here should be on the same side, okay? All right, now it's time. That's the only thing we determine. So let me show, now we're gonna build a molecule to see what will be our final product, right? I like to show this so that we know exactly. As a matter of fact, it's the same thing. That's how I'm gonna be breaking the bond so that you can see what's gonna be happening, right? It's the same thing. The arrow can be reversed, it's the same thing. Okay, let's go and build that molecule. Okay, guys, so here's the molecule after I build it, okay? So the same thing, you see that OCH3, everything seems there. The only thing I added was our hydrogen group. This is an hydrogen. Hydrogen, it's outside, inside. I'm just putting inside and outside. It's gonna be important soon, okay? Forget about it. But again, I just showed the hydrogen. See the hydrogen, OCH3 and the carbon is present here, right? Now, it's because that's the same molecule we were saying. I just want to make sure this is our oxygen group so that, oh, our double bond look like this. It's hard to tell, but let me remove this. It's gonna be easier. You see how you can see the double bond? It's hard to tell, but the only thing I want to see is why I will be drawing my stereochemistry the way I will be drawing them after, okay? So let's do this. Normally, it's not what you think. The molecule isn't gonna come like this and click, cyclohexene. No, it's either gonna come, the dienophile, for example, will either come from, oh, I'm trying to fix this. It will either come from the top or from the back, okay? Now, two things can happen. We already know that based on the charge, carbon 5 is partially negative. This one too, but we don't really care about this one because it's too far. Why would it go there, right? If there's a nice one, carbon 5 is waiting right there to interact with this partially positive charge, carbon, right? So I know that this will have a nice way, less steric enriched. It's not gonna, it's nicer here, right? We know that this will be at some point the orientation. We want oxygen and that OCH3 group to be on the same side, right? But the dinophile can do this too. Like a hand. That's why I was talking about the hand. When it's, I like, pick a side, guys. Pick a side so that whenever you're gonna be drawing it on the exam, you always get it right. I always love to make my dinophile come from the back. You know why? Because when it's gonna come from the back, anything inside my Y, when I'm saying inside, that's what I was saying here. This is the fork. Let me see the Y. Anything inside the diane, you see the nice Y fork, anything inside will point up and outside the diane will point back. Let me show you what I mean. We'll put down, then back, down. But anyway, let me show you guys. First, the dinophile will come, that's the dinophile. It's gonna come from the back. But remember, two things can happen. It's either it comes this way or it rotates and come this way. The endo rule say that it will form in a way that this group here outside the diane, let me put it here. At the end, after closing the ring, this group outside will be on the same side as the outside group of the dinophile. And the best way we can achieve that is to make them interact in this way. Remember, that's what the teacher is showing you. But in reality, the molecule will interact like this. It's gonna flip, interact like this. Now, let me show you why. After interacting, it's gonna come, zzz, and then let's break the bond, okay? Quickly. I'm just keeping it, I know it's gonna come like this. I'm just gonna break the double bond to do that nice concerted mechanism we talked about, right? So let me break this bond, and you see how, pay attention to this hydrogen, how it will naturally go up, because remember carbon is tetrahedral, right? So let me remove this. From a planar structure, if you break an alkene, look at this, it's naturally, I'm not even touching, I haven't even connected it yet. Okay, it's naturally going up. Okay, let's keep going. We know it's gonna attach in this way. According to the endo rule, I'm gonna remove this because this is come from the back. Okay. Oh, I'm connecting it. I'm not touching it, I'm just connecting them together. And of course, this one will break from the back. Oh no. Okay, it's okay. All right. I connect this here, right? And this bond that just last bond will go this way. Oh, okay. All right. And that's what we get. Anything that was inside the fork, guys, this is the final. You see that CH3, it's even hard to tell. Anything that was inside my diene, anything that was inside my diene is pointing up, and anything that was outside is pointing down. I stick with this because I know that whenever, if a dinophile attack from the back, my group inside should be pointing up. And of course, if you choose that your dinophile will be attacking from the top, then it should be the opposite conformation, right? But I like to do it that way. That's my way of doing it. It's easy. It's easy for me to visualize in my mind. Once I know this, the endo rule is saying that the reason that the molecule, the dinophile flip, is that at the end, we want the OCH3, like the outside group of our diene and the outside group of our dinophile should be on the same side. So that means if this one is pointing down, that one will be pointing down. You see, look at this. Look at what I did after closing the ring. This one is pointing like in the back, like down. Guess what? That's an hydrogen. I did put the hydrogen. That's the hydrogen. I try to avoid to put too many hydrogen on this final because we already know the hydrogen is there, right? But here, to make it nicer. This group here with the double bond, it has to be facing, it has to be down to according to the endo wall. Okay, both are down. I know that my molecule is stable. But guys, don't worry too much if it's hard to understand this molecule. We're gonna draw it again, but that should be exactly like here. I try to number it for you. You see, one. Oh, it's hard to focus. 1, 2, 3, 4, 5. Oh, that's a 6. I don't know why this not. It's showing like a 5. Yeah. You see, I numbered it 1, 2, 3, 4, 5, and 6. We're gonna draw this compound. Okay, let's do this. Let's go back on the paper. Okay, so we're back to our board here, right? Again, I know that based on what the teacher gave, it's easy to think that that's how it's gonna click. But according to the endo rule and what I was showing you, our molecule here can either be in this conformation in this solution or in that one. But to respect the odd endo rule and make sure that OCH3 and those outside group here of the dienophile will be on the same side, I have to pick this version. And what I'm saying outside is because if there's a symmetry and in reference to this ring being closed, right, to whatever is gonna be happening here, we know that this group here, that ketone and that metal group is outside, okay? But anyway, so really in reality, let me copy this, let's draw a molecule. That's what's gonna be happening, okay? So let me do it small so that you can visualize in your mind that it's approaching from the back. And of course, like we said, let's quickly make sure that every carbon is number 1, 2, 3, 4, 5, and 6. 5 and 6, right? 5 and 6. And of course, let's draw interaction so that we know that's what we want. So this one will do this, that will, this, and that, and this. And we're gonna draw, let's get to our last step into drawing the molecule, right? So the first thing I do to make it easy is to go to my nice, when we say both structure, look guys, you do 1, 2. It's like 2 hat, I guess. You connect it together, right? And then quickly put number of carbon 1, 2, 3, 4, 5, and 6. You see, I'm only drawing this backbone here. Okay, what I'm trying to make, what I'm trying to produce. And of course, now let's make sure that it's complete. Let's add whatever is missing. Okay, we know that based on this interaction, 1 and 2, a new bond should be created between 2 and 3. So I will place a bond here between 2 and 3. I also know that if my dienophile attack from the back, anything inside should point up. Inside, remember there's an hydrogen here. Anything inside my diene will be pointing up. So I will put hydrogen here and my metal group pointing up. Again, if you want, you can write CH3, but again, I'm hoping by that time, everyone, like right now, if you're watching this, you're familiar with the line bond structure. And of course, our OCH3 is pointing down. Anything outside, remember, outside of our diene should be pointing down. So I'm gonna draw it going down. No, it's hard to draw this going down, but you get the point, right? Going down. It's gonna be in the back or going down. Some people will draw it. It's, guys, you understand. Now, carbon 6 and 5, according to the endo rule, that's why I follow it. This OCH3, because it's pointing down, you can even do OCH3 pointing down this way, guys. But it's hard to tell. You have to have a nice mind to understand that what I mean is like it's pointing down like this, OCH3. 6, okay, for carbon 6 is attached to that nice group. It has to be pointing down too. And on carbon 5, the metal has to be pointing down. Let me place back my number 5 and 6. And if you want to check, make sure that this is pointing down according to the down and down. Oh, I'm like, okay, all right, I followed my rule. The outside group of my diene is ended on the same side. The back, like, you know, it's pointing down, just like the outside group of my diene is pointing down. Both are pointing down. I know that I respected the endo rule. Okay. Now, before we end, real quick, I want to show you. Wait, make sure that verify your work. Make sure you put every group to, okay. 5, 4. Okay. One last thing I want to do. Just something. It's the same thing, right? But I want to play around a little with this in case you see something new on your exam. Guys, I know here before we had H and a metal group, right? But let's remove this. Let's think, for example, we had, like, it's just another CH3 here, right? Let's think about it. Guys, it's still another additional group. Don't let yourself distracted by it. Remember, this is still inside or diene. So yes, my backbone will still be the same thing. My backbone, it will still be the same thing. The only thing I would have added here, because remember, this CH3 here is connected to carbon 1 and carbon 4, right? So I'm gonna make sure these two are connected. So that's our CH3 here. You see how it looks complicated, but it's not. So really, once you know what it is. Now, for both, once you have this nice both conformation, you can transition to the other classic way, right? First, I'm gonna do my 6-member ring, right? Quickly, number 1, 2, 3, 4, 5, 6, making sure that 2 and 3 as a new bond, right? 1, OCH3 should be pointing down, so I'm gonna write OCH3. Let me move this up a little. On carbon 6, this group should also be pointing down because that's the endo rule, right? If they both should be these two groups should be on the same side, even this one too, but anyway. 5 is pointing down. You see of 6 and 5 group, the group of the dienophile are pointing on the same side as the outside group of the diene, so that's what. So it's important. And 4 is pointing up. Remember, this is 4. It's pointing up, so I'm gonna do this. And that's how I transition from, you know, the two structure. Same thing here, guys. If you have this, everything is almost the same, except you can draw. That's so hard to. Okay, here it is. You can do this just to show that there's a carbon here. And of course, I like to show the stereochemistry. I will make this a little darker so that they know that I mean that this CH3 is pointing up. Okay, and that's pretty much it, guys. And that's how I found the product for my reaction. Okay, that's all I have for you. Thank you for watching. Bye.